For this problem, we're starting out with not the percent that the concentration is changing by and not what the initial dose is. And going to the equation, we're starting with the equation and deriving from that what we know about the medication, its initial dose, and how quickly it breaks down in the body. So the first part, the initial dose, remember in a exponential function, this first number, a times b to the x, this is your a value. That's your initial dose. So it must be 80 milligrams because that's the y-intercept. That value in an exponential function is always the y-intercept, the value of y when x is 0. So that's our starting amount of medication in the bloodstream. But this one, you want to be careful. When you see that 0.75, you want to look at that 0.75 and think, oh, easy. So the medicine is processed at a rate of 75% each hour, and how much remains in the bloodstream after each hour. But be careful here. You want to think if you multiply something by 0.75, so for example, if you take your 80 and you multiply it by 0.75, what you're actually left with is 25% of that. So if you do 80 times 0.75, you get 60. Okay, and so you've got 75% of it. Remember, what this means is you have 75% left in your bloodstream. And this is asking how much of the medicine is processed each hour. So if, in the first hour it goes from 80 milligrams to 60 milligrams, that's a 75, 60 is 75% of 80. That means that 25% has been processed. So when you go from 80 to 60, you're going down by 20. So if it goes down by 20 milligrams out of 80 milligrams are processed, 20 out of 80 is 0.25, or 25% is gone. So you want to be careful. It's usually going to be described as how much is processed each hour. So if 25% is processed and metabolized by your body in an hour, you have 75% left. Multiplying by 0.75 gives you what remains in the bloodstream. 25% is what's been removed from the bloodstream by your body's metabolism. So just like we were talking about the doubling period with exponential growth, when we talk about exponential decay, this concept of what happens to the halving period over time is also a really important concept. So the halving period is, how long does it take for half of the medicine to be processed? So we want to know how long does it take for the 80 milligrams to be cut down to 40 milligrams, and then be cut down to about 20 milligrams and 10 milligrams. So we're wondering how long does it take for it to be cut in half each time? Now, hopefully at this point you're predicting that it's the same amount of time for each interval for this to happen. So if you take your exponential equation, you do 80 times 0.75 times 0.75 times 0.75, you'll notice that you have to do it between 2 and 3 times for each of these. So it's between 2 and 3 hours. Cut in half. So if you do 80 times 0.75 to the 2, it hasn't quite gotten down to 40. 80 times 0.75 to the third power, it's a little bit less than 40 milligrams is left. Then when you go down here and you go from 40 to 20 milligrams, you'll notice it takes another 2 or 3 hours. 2 or 3 hours. So there's a couple ways to explain this. So first of all, is we're prone to thinking of things linearly. So you would think, if it took 2 or 3 hours to go from 80 milligrams to 40 milligrams, then going from 40 to 20, which is a much smaller change, wouldn't take as long. But remember, when we're talking about exponential growth, the slope is changing as you go. So that first jump from 80 to 40 might be this interval up here, takes 2 or 3 hours. But instead of it going faster, going from 40 to 20, some smaller amount of time because it only has to go down by 20 milligrams, not by 40 milligrams, you think it would go faster. But remember, even though it has a smaller amount to drop to cut in half, your line has a flatter slope, so it's not going as fast. Just like before, those two things balance out. Then going from 20 milligrams to 10 milligrams, that's only a change of 10 milligrams. Seems like it wouldn't take as long as it took for it to drop by 40 or 20. Remember, at this point, your line is even flatter. So even though it doesn't have as far to drop to be cut in half, it's not going as fast, and those two things balance out. You could also think of this sort of numerically as well, thinking about that pattern, just like when we talked about the doubling period with growth. If you take that decay factor, 0.75, we're starting with 80 times 0.75 times 0.75 times 0.75, and so on. Each of these times I multiply by 0.75 represents 1 hour passing. So you've got your first hour, second hour, third hour, fourth hour, fifth hour, sixth hour, and so on. And any stretch of 2 or 3 hours, so if you take this 0.75 to the power, I think it's about 2.4, 2 and 3, is equal to about 0.5 or 1/2. So any stretch of about 2.4 of those, no matter where you're starting, about 2.4 hours later, wherever you're starting, it's going to be cutting that medication amount in your bloodstream in half. And it doesn't matter which set of 2 or 3 hours it is, beginning, at the end, any stretch of about 2.5 hours is going to take whatever it was at and cut it in half.